Hi, sir. Good morning.
Good morning. Good morning. So let's wait for maybe say 2 more minutes.
Okay.
I think everyone will join in soon. Meanwhile, I'm just loading the data and splitting it up into train and test.
Okay. So how many more sessions do we expect, Sanatan, for this machine learning?
Probably 3 to 4 more.
And then NLP?
NLP will be 2 to 3 sessions.
So any idea, like you will be only taking NLP?
I'll be taking NLP. Yeah.
Okay.
Okay, I'll start at 9:05. I don't think many people will turn up, or usually they are late.
Okay.
Okay. Sorry, I'll just revisit what we call as oversampling. I think this is what we did last time, right?
Yes.
Okay, so let's do this oversampling part. Okay, I think you are the only one right now. Okay, let me print the distribution before.
Actually, like today's session, it's not there on Zen portal, and there's no mail also for today's session's link. So I think that might be the reason for people to.
How come did you get it like?
I used yesterday's session only. I tried with that, and then.
Oh, okay.
But I think it's same for a week.
Oh, I think it's the same for every month.
Okay.
For the mentor, right?
It's the same. Yesterday's link only from the mail and that.
Okay. Would it be okay for you to interact with me? I don't think others will join in that if there is a confusion like this.
Yes.
Okay, got it. So, all right. So this is the distribution before, and I'm going to fit and resample onto this data. Which model do you want me to use? So accordingly, I'll decide whether to scale
or logistic regression.
Okay, see, decision tree would not require scaling. However, it is also what you can say is, I mean, it can accommodate even data sets which are kind of biased. So
Yes.
It doesn't make sense to use a decision tree just to show the impact of it.
Okay.
Okay, because if you just duplicate, right, a sample will fall into the same partition.
Yeah. Okay.
Right. So for oversampling, it doesn't make sense. So let's use, say, logistic regression, and then we will, scale it as well. Yeah. So let me scale this also.
We did implementation of oversampling.
Yeah, I'm just showing you because I will be showing you the hybrid also, right?
Okay.
So I need that again. So let's scale the data. Okay, I'm saving it back to test and train again. That way, the variable names remain unchanged. So, okay. Let me fit and resample. Okay, this is just to show you that if you resample, this is what you get. Okay, and these are the results afterwards. So you can see that like before the number was 148 and it got increased to 250. So this was oversampling. You are increasing the minority class examples. Today we are going to see undersampling. So this we had done in the last class. Let's go with undersampling. The concept is the same, but I mean, it's a reverse of what we did. So we are going to reduce the samples in the majority class. Please note that oversampling is also called as ROS, random oversampling of examples. Okay, this is a special name. Undersampling doesn't have any special name. So ROS is random oversampling of examples. Okay. So in undersampling, you go to this IMB learn, go to undersampling and import random undersampler. Okay. So the objective is to reduce the majority class. And this time what you'll see is I'm going to keep the sampling strategy as 1. So I'll just highlight this. Okay. So the number of resultant samples in the majority class, they are equal to, okay, they are equal to the number of samples in the minority class divide by, okay, this sampling strategy. Okay, this is what it is. Sorry, just give me a second. Okay. Yeah, this is what it is. So if sampling strategy is 1, what would be the number? How many samples will you get in the majority?
Same as minority, 148.
148. Okay, so you'll see that. So it has now become 1 has become 148. Okay, makes sense. Let's say I make it 0.5. What will be the number now?
Half of 148.
No, not half of. It will be twice of. Yes or no? It would be twice of that, right?
Yes.
So if it is twice of that, what is the number? 296.
Yes.
But
Yeah,
do we have 296 examples?
No.
See, if you are increasing 250 to 296, is that allowed? Your job is to reduce it, right?
Yes.
So it will throw an error. See this. Okay. It will say that consider increasing the ratio. Okay. So the question comes again, what should be this least sampling strategy?
Ratio of majority
divided by minority. It should be minority divided by majority. So this is the least ratio possible. Okay, least sampling ratio. In this case, it is, let me just put a comment here. So this would be 148 divided by 250. Okay, anything greater than this would be acceptable. Okay, around, let's say around 0.6. So just to show you, if I have this 148 samples and divide by this 0.6, okay, the number that I get is 246. So this is acceptable. So you have just reduced how many samples? 4 samples.
4 samples.
Okay, so this is acceptable.
So in both cases, the ratio is same, minority upon majority. The only thing
No,
is
no, no,
we
no,
are
no,
multiplying
no.
the strategy.
Is it the same?
Yeah, there we were multiplying. That is why it was increasing, and here we are dividing that.
Dividing, yes.
So the sampling strategy ratio remains same.
Ratio is the same, but I mean, the way you should perceive it is this. See, whatever you are trying to change, right? It has to be changed from the perspective of the other class.
Yes, yes.
Okay. See, the formula of majority is actually dependent on the minority class. Similarly, for minority, it is dependent on the majority class.
Yes.
Okay. So we have to keep that in mind because this can confuse someone, right? Here it is division, and there it was direct multiplication.
So reduction is always a division operation. When we divide,
Yes.
we reduce the quantity.
Yes, you're right. See, you can grasp these things, right? But for others, sometimes it may be confusing. Oh, we do have now 7 participants. All right. So this is your undersampling. So let's try to create a hybrid of the two. You can always train a model before and after, and then you see the results, right? Do you want me to do that? Okay, I'll do it. Let's go with, say, logistic regression. Let me put a random state so you also get the same result. I should have put a random. Oh, I did. Okay, that's fine. So this is my sample data, which has been standardized also. Okay. And now I'm going to compute, say, accuracy score. So this is before undersampling. So let's go to this metric. Let's go with, say, accuracy score and compute the accuracy of your model on the test set. So use the predict function to get the predictions. Let's see if there's a problem. So this is the accuracy score before undersampling. Okay. Now I'm going to do it for after doing the undersampling. Please note that the current ratio is 0.6. The current ratio is 0.6. Okay. So I'm going to fit it onto resample data. Okay. And did it increase or it stayed the same, right? Do you see that it stays the same?
Yes.
Okay. So like if you look at the, the ratio right now, it is, just 4 samples. I didn't run this. Okay. So from 250, it has been reduced to just 246. Okay. Maybe let me make it closer to, say, so I'll run it for different sampling strategies. Okay. So my sampling strategies are this. I'm going to try, say, from 0.6 onwards, I'll go up to 1, maybe choose 20 sampling strategies. And then I'll simply check. So give me this random undersampler. And then we will resample the data using this random undersampler. And then we fit the model onto this resample data. So here you just change this to J. Compute the accuracy score. You need to store these accuracies in a list or some other data structure. I prefer a list because it is easy to work with. And then you append these accuracies here. Okay. So these are your accuracies for different sampling strategies. Let's see if we get some better results. Okay, so this is the results that we get. You can see that our accuracy has improved slightly, right? From 95.9, it was the same as earlier also. Okay, it has now jumped to 96.491. Let's try to figure out for what sampling strategy this was the value. So let's try to get the index of this. So let me get the first index of the maximum value. So at this index, you got the best results. So I have it in SS. So SS of this index will tell me this is the best sampling strategy for the given test set. Okay. So this is the sampling strategy. So let's see how many samples are there. So we have how many samples in the minority class?
Minority is 148.
148. So 148 divided by this number is going to give me the number of samples that were present in the majority class. So these were the resultant majority class samples. So it was reduced to 209. All right, so this is your undersampling. I'll show you now how to implement the hybrid. So I'll be implementing the hybrid approach. So in the hybrid approach, you can actually implement oversampling first and then undersampling, or you can do the other way around. Okay, so you can take one of them first and the second one next. But you need to keep in mind that sampling strategies will affect how many samples are going to be created. So they might throw an error. So keep the track of what is the appropriate sampling strategy. Okay. So now I'm going to implement two things. Okay. So I'll start from scratch just to show you. Okay. So this is my data. I'm putting everything from scratch. Okay. So this is your data. Let me split it into train and test. So we have split the data into train and test. Let's standardize it. Instead of standardizing it, so, okay, what do you think? How many steps do we have to do? Think about it. How many steps do you have to do? See, you have to standardize, you have to undersample, you have to oversample, and then you have to build a model on it, right? Okay. So what do we need?
Pipeline.
A pipeline. Okay. So in IMB Learn also there is a pipeline. Just like sklearn, there is a pipeline in IMB Learn also. So you can use either one. Okay, both will work. So this is just to show you there's a pipeline here as well. So here you can pass the steps. So let's define the steps. You can call them my steps. So every step is a tuple. So the first step would be to scale the data, right? So I'm going to scale the data. The next step is, what do you want me to do next? On undersampling or oversampling?
Over.
Okay, let's go with over. So let's call it, say, random oversampler. Okay, so we have to provide a sampling strategy here. What number do you want me to keep? Okay, let's discuss what is about to happen so that you have an idea. See, this is the before ratio. Okay, keep this in mind. This is the ratio of the samples in the train set. So if I do oversampling, which means that I'm going to increase this 148, right? Yes or no? Does that make sense? Oversampling means duplicating the minority, right? So if I increase this number, say, to 250, do you think it will allow me to undersample later?
No.
No, right? There will be a problem, right? Because both are now equal.
Okay.
So if you try to, so I cannot reduce it too much, right? I mean, I cannot increase this minority class too much. So give me a reasonable number. Okay, give me a reasonable number.
0.7.
Okay, let's go with 0.7. So let's see how much 0.7 will give us. So 148 divided by, okay, so 0.7 into 250 is how much?
Multiplied by.
Yeah, 0.7 into 250 is how much? 175. So if I say 0.7, this will now, 148 will now increase to 175. Does this make sense? So after this operation, this will be 175. Okay. Now let's try to do undersampling. So this is your random undersampler. And let's discuss, okay, how much reduction we want in this 250. So how much reduction do you want in 250?
So in now this after random oversampling, this becomes my base count?
Yes, this becomes your base. Yes.
Okay.
So how much reduction do you want now?
200 I want, so I will
Okay, so if you want 200, then you can do this number, so 250 divided by 200 divided by 250, whatever this number is. Okay, so this is 0.8. So if you want 250 to become 200, you will keep this number as 0.8. Does this make sense?
yes.
Okay, so now the resultant will be like this. Okay, so you are checking for this ratio. Okay, you are checking for this ratio. So this is the resultant data that you have. Okay, and then finally, I will apply any model. So my model is logistic regression. So let's call it, say, LR. Okay, I'm giving a random state, so you get the same results as well. Okay, so these are the steps of your pipeline. Provide these steps here. Okay, well, let's call it, say, our pipeline, and then we will just train a model with this. So we are fitting this onto our train set. So pipeline has been fit. Okay. So once the pipeline is ready, you can actually test. Okay. Now, please note that for you to test, do you think I need to pass the pipeline? When you are testing, do you think you have to pass the pipeline? No, right? What is it that you have to use? Just this.
Model.
Okay. Just this, right? Yes or no?
Yes.
Okay. So you'll be using to, I think I should have done, we need actually scalar also, right? We need actually scalar also, right? Okay, I mean, we need to transform the data also, right? So this is your pipeline. Okay, I need the two steps. Okay, I need the two steps. So one would be your, I'm thinking, okay, whether I should have done the scaling outside, because that will make it easy. Okay, let me see if there is a way, if there is a hack to do this. Okay. So I need, so the following steps. So if I do just like this, okay, it gives me the standard scalar. Okay, that's one thing I need. And I need one more thing, which is this LR, right? The logistic regression model. Okay, sorry. It doesn't work like this.
One
Okay.
bracket. One bracket.
No, I have already given one bracket. So just a second. I'll have to access them, I think, one by one. Okay, is there a way to hack it? Does it ask like a tuple? No, okay. So you have to, access it like this only. I mean, if there's a single element, you can access it like this. But I'm thinking, okay, how to access multiple elements? Okay. Anyways, this is fine. So this is my first one. This is the first step. So I can transform my data, okay, using this standard scalar. This is my test set, right? So I transform my data and get the transform test set. Okay, and then I can, what we say in this pipeline, I need the logistic regression model to predict the results. So m underscore pipe of this logistic regression. And then I use the predict to get the predictions. Okay. So predictions are on this transformed X test. Okay. So these are your predictions. Let's, directly compute the accuracy score from these predictions. So pass the actual values which are in Y test. And these are your predicted values. So this computes the accuracy score. So this is 96.491. What was the result previously? So do you see that, like, when we computed the hybrid, right, we are getting like very close to the best results. Okay. Like, and the one without was around this 95.906 without doing anything. Okay. Without doing anything, the results were 95.906. Okay.
Will my this accuracy value change if I change the order of over and under sampling?
Yeah, this might change because the number of samples would change, right?
Yes.
So that would also impact, right? So we have to be very careful about what you do. Okay. So you can try the reverse also and put different values of appropriate sampling strategies and get the results. Okay. So this is how you can implement the hybrid, and you can see it is helping in terms of like just, I mean, if you combine the oversampling and undersampling, it helps in improving upon the original condition, the original scenario. Okay, let's now, so before I go to SMOT, any questions? Anyone with any questions? Yes, people.
Like we have grid search CV, can we use that also here to see whatever is the best sampling strategy?
Yes, you can. You can. So it will just become a little complicated. It will just become a little complicated. Do you want me to do that?
Yes.
Sure, I'll do it. It becomes a little complicated though.
Maybe
Okay.
we can use
Yeah,
random search
that's
only.
okay. I'll call randomized search CV in that case. So I'm going to create my hyperparameters. Let's call the stratified k-fold. Typically, for bigger data sets, I would not advise you to run this stratified k-fold. The reason for that is you already have enough examples in the test set. Even if you randomly split, right? Don't you think you have enough examples?
Yes.
Yes.
So for bigger data sets, you don't need this. Okay. But for smaller, yes. Okay. Because if the number of samples are small, then you don't get a good estimate. Okay, I'm going with 5 splits. So every test set has 20% of the data. So there is no parameter for standard scalar. We have one for this random oversampling. So I'm going for some of the random oversamplings. Okay, see, the advantage of this is this. The advantage of using hyperparameters is you take this ROS and provide this sampling strategy. Okay, strategy. All right, and then you can give some numbers. So I'm going with some numbers. Say starting from say 0.65, I'll go up to 1, maybe 10 values in between. Okay. And then I will do say random undersampling. Yeah, let's copy this whole thing. I'll give the same. Okay. But I'll just call it random undersampler. Do you want to give any logistic regression hyperparameters?
No.
Okay, so is this enough, right? So the advantage of this is even if it fails, right, it will just ignore those, you can say those particular values of sampling strategies where it does not work.
It will not throw an error.
It will not throw an error, in my opinion. Okay, as far as I remember. Okay. So what we'll do now is let's call this randomized search CV.
Should we remove these sampling strategies that we have hard coded in the function call? Or it will.
Oh, yeah, it will not have an impact. It will just be replacing them.
So
It will just
hyperparameters will have the priority.
no, it just replaces them. It just replaces them. Okay, it will just replace them. Okay, I'm just putting this random state here, so you get the same results. See, because the sampling is done randomly, right? So put a random state here also, so you and I get the same results every time. Okay, let's call this pipeline here first. You have to specify the hyperparameters which are there in param distributions, since we are doing randomized search CV. Okay, and give this as the hyperparams that you made. The cross-validation technique is stratified k-fold. A scoring metric is, let's say, accuracy. All right, and you can just say this is RCV, and then you fit it onto your data. I'm fitting onto the entire data, okay? And since we are doing 5-fold, I just need to know the best hyperparameter combinations, okay? So this has done. Do you see it didn't throw any error?
Yes.
Okay. Do you want me to show that it throws an warning for those sampling strategies where it doesn't work? I have actually reported this. That's why it's not throwing any warnings to you.
Yeah, can you comment it out and then show like
No, but
what's the...
it has already imported it, right? So even if I comment it,
okay, fine.
it cannot. I mean, do this, right? I mean,
Okay.
I would want. I mean, I would
Can
have
we
to restart my
change-
kernel.
Okay.
So can we change this ignore thing to something so that it does not ignore the warnings?
No. I think yeah, there must be something. Some
There
argument.
must be something other than ignore because
Just a second. Let me see if I can. Let's put it to default. Okay. Let's see now. Hopefully, if it is running for, do you see that it throws a warning? Some of the values are nans, right?
yes.
Okay, so it is giving an indication that some fits failed because the sampling strategy, see, maybe for oversampling, it says that your majority class, while trying to remove samples, the ratio was not appropriate. You have to consider increasing it. All right, makes sense? So it doesn't, it tells you how many fits have failed. So 25 of the fits have failed actually. So 25 combinations which it tried. So it's not trying all of them, right? It's trying a total of 50, you can say total combinations. So I'll tell you how much how much it actually tried. So how many in reality do we have? So we have 10 into 10, right?
100.
100 into how many times you are going to run it? 5 times. 100 into 100 into 5. Sorry, 10 into 10 into 5. So that is 500, right?
Yes.
So out of the 500, it picked 50. And out of those 50, 25 of them failed.
Okay.
So the values that it selected, okay. So you can essentially say that it tried 5 combinations out of 100. Sorry, 10 combinations out of 100. 10% of it tries. So random selection, randomized search CV, it tries 10% of the combinations at random. So out of these 10% combinations, each is going to run 5 times, right? 10 into 5 is 50, right?
Yes.
So out of those 50 combinations, 5 of them failed.
Yes.
5 of them did not satisfy the threshold, the sampling strategy values that you provided. Okay. But anyways, you can actually put it to ignore and you will not see such warnings. So these are your best params. Okay. It is showing you that, okay, it is deprecated. Maybe this particular function in my case is deprecated. Okay. And sorry. And this is the best score accordingly, around 97.5. Okay. So you can try running grid search on it. It will further it will definitely be as good as this. Okay. But it can improve upon the results as well. Okay. So do you want me to keep this as it is, or do you want me to put ignore there, and what do you recommend?
Yeah, we've seen the errors, right? We'll ignore it.
Okay, just ignore the errors in that case. Okay, so this is your hybrid. Let's run your what we say SMOT. Okay, so to run SMOT, I mean, it's there in the same library. So you go to this IMB learn. Okay, go to oversampling because it's an oversampling technique, and you import this SMOT. Okay, synthetic minority oversampling technique of examples. Synthetic minority oversampling technique for examples. Okay. Now, To SWOT, you provide the same thing, the sampling strategy as you did for a simple oversampling, for random oversampling. It's the same thing. Okay, so you provide a sampling strategy. So this will tell you how many samples you want to create. Okay, so is it okay if I show you the difference through a visualization? What do you recommend? So
Yes.
that you can see it is creating duplicate, and it is not creating duplicate samples, but others are. Okay, shall we do that?
Yes.
Okay, so I'm going to show you your X-Train. This is your X-Train, by the way, right now. Let's get two features from it. Okay, I'm going to get two features right now. Maybe say feature 0 and feature 1. Okay, I'm going to get the first two features. Okay, these are the first two features. And now I'm going to plot it. Let's say this is my input. Okay, and now I'm going to plot this. I'll import, I have already imported Matplotlib before. So let me plot the scatter plot for this. So input of the 0th column and input of this first column. Okay, let's see. So this is how the data looks like. Kind of very weird. Do you want me to reduce some of the samples?
Yes.
Yeah, that'll
Okay.
be easy.
Okay, let me say the number of samples that I'm doing are, say, the first 50. Okay, so this is how the data looks like. Let me color it. So I'm going to, I'll just mention it. Okay, taking the first 50 samples and first two features for visualization. All right. So your color will be in white rain. Since I'm taking the first 50 samples, I'll just say, okay, this is 1 second. I'll just write it like this. So the first 50 samples are in out instead of doing it here. Okay, so this is how your data looks like. Let me show you, okay, which do you think will be the minority? Which do you think will be the minority?
Here 1 would be the minority.
Here 1 would be the minority. I hope you remember. It's the same data set that we picked yesterday.
Answer.
Okay. Let me plot the legend also. Yes. So I'm creating this list of unique values. I hope you have realized by now, like most of the things that we do, they are repetitions, right? If you know, once again, let me check. So if you know the algorithm name, then you can implement, just a second, then you can implement almost anything. This handles. Okay, so this is the data. You can see that. Okay, it doesn't look like something is in the minority, right? Okay, let me see. Okay, let me see. What is the exact number? Okay. I mean, so it is fairly equal. Okay, let me increase the number of samples. Let me actually do it for the whole thing for white rain and then see what is the distribution. So it is around 148 to 50. So I should take, shall I take all the samples? Will that be all right? Or shall I shuffle it? I think I'll shuffle it. Okay, that will be easier. So I'm going to shuffle it. So I have how many samples? So they are in white rain. So these are the number of samples. So I'll just show you what I'm doing right now. Okay, I'm selecting a list of 50 random indexes. Okay, I'm selecting a list of 50 random indexes. Okay, see this. I'll just print this out. Okay, these are 50 random indexes that I'm going to select. okay, from this data set. All right. So I'm going to select these 50 random indexes. This might change slightly because my NumPy seed is not fixed. Okay. I mean, you want if you want, you can fix the seed also. You can simply say numpy.seed and put a random number here, and whichever you can say random number generator you are using with NumPy, it will now generate the same thing. Okay, so I've generated these 50 indexes. I'll just pass L here and this L here. Okay, so it will select those samples and it will show you the distribution. 1 second, there's a problem here. Okay, it's called as numpy dot. Okay, 1 second.
I think it's random seed.
It's random seed. Underscore is there or what? Or is it random dot seed? No, just a second. In NumPy only there is this seed. Okay, I have to see. Okay, it has to be passed within brackets or like how? Okay, it's numpy dot random dot seed. In NumPy there is this random and then there is this seed. Okay. There is the problem here. What does it say? Indexing arrays could not be broadcasted with 50 and 2. Why? Okay, just a second. Let me print what L is. Okay, this is the list L. Okay. It is showing at this time. So it is not asking me to select. Just a second. Okay, and now if I take the 0th, it gives me the 0th row. Okay. Oh, I think it will not allow me to do this if I'm passing a list here. Is that so? Yeah. Okay.
Can I do 0:2? Then it will give me this 0.
But this should also be allowed, right? Like I understand what you're saying. So okay, I get it now. In NumPy, there is this problem. Okay, please note this. That you cannot do like simultaneous picking of rows and columns. So you can pick rows first or columns first. Okay, so I'm going to show you how you can do it. So a simple way to do that is this. Okay, so first take the 0th column. Okay, and then you take the first column. Okay, which is say this. So this is the 0th column, right? I'm going to take the first column. Okay, which is L comma 1. All right, so this is 1 second, and I'll concat it. Okay, 1 second. That's a easier way to do it. Okay. So numpy dot. I think we have this function vertical concatenate. Or do we have to horizontally concatenate? Just a second. Let me think. A vertical would mean side to side, right? Yeah. Okay, let's see if it can do this. Give me a second. Oh, it's not in NumPy. 1 second.
It's concatenate and then we give the access.
There are actually multiple functions, vcat, hcat. Okay, maybe it's not in NumPy specifically. But yeah, you can, you're right, you can do that also. You can give concatenate and then provide access here. So my access would be, do I have to match it row wise or column wise? If I do 1, then it would be matching column wise. So 1 after the other, it should be 0. Okay. Just a second, let's see. Okay, give me a sec. All right. So, 1 second. I just need to check this. Does it look like 100 elements? Does this look like, yeah, this is 100 elements. Okay. So I have to match with like this. I think I have to pass this data. That would be like this. Okay, just a second. Okay, got it. What's the problem? Okay. See, there is no access as such, right? So I have to reshape them. Okay, now this will work. Do you see that? So this is the hack that you can try. Okay, so this is the data that you have. So this is your input rather. Okay, so this is how the data looks like, and you can clearly see that 0 is the minority right now, right?
Yes.
Typically, zero is the majority. Typically, yes or no?
Yes.
0 means healthy, right? 1 means people having a disease. Yeah. All right. So now I'll show you. Okay, if you do oversampling, okay, so undersampling will reduce the majority class examples. You will see less yellows here. Okay. Do you want me to show for both undersampling, oversampling? Suggest, please. Do you want me to show for both?
Yes.
Okay, let's go with, say, first undersampling. Okay. So take this random undersampler and say a sampling strategy is say 1. Okay, so you will see a lot of reduction in yellows. Okay. And then I'm going to fit and resample from this data that we have, which is an input and output. Okay. And let's say this is my resampled data, resampled input, resampled output. And I'm going to just plot this. This is your undersampled data. So this would be resampled input. And this should be resampled out. Okay, and this time we can call it undersampled data. Okay, so you can see that now yellows have been reduced significantly. Yes or no? Compare it with this.
Yes.
A lot of yellows have reduced. Now, let's see for oversampling. So this time you will not see any difference in the first plot and the second plot. This plot, I'll just keep it below so that you can see. Okay, so difference between original data and oversampled data, there will be no difference. Okay. Can you reason why? Why would there be no difference? Yes, people. Why do you think there will be no difference?
Because duplicates will be created and it will overlap on top.
It will overlap on top of it, right? Overlap on the purples. Okay, so you will not see any difference at all. Okay. Okay, I hope you can see it now. I'll just reduce the size. Okay, do you see there is no difference?
Yes.
Yes.
Let me just show you the difference in the samples. Okay, so I'm printing this resampled out.shape. Okay, this is going to tell you how many samples do I actually have. Okay, do you see we have 70 samples right now?
Yes.
Okay, and let's see how many samples were here. How many were here? 50, right?
Yes.
I mean, you know that the actual number, right? I'll just print this here. Okay, do you see it was 50? So what you did here is like you increase the number of samples. Okay, from the minority class, you created a lot of duplicates, but duplicates are lying on top of them. So you cannot see the difference. Okay, you cannot see the difference. Is that part clear?
Yes.
Okay. Now I'm going to do smart. So I'll just keep here. Just a second, I'll increase the size also. Strategies. Okay, now let's go with smart. So in smart, you will see a lot of purples lying created in the middle. Okay. So let's take this SMOT. I'm going to call it, say, SM. What are the hyperparameters for SMOT?
Neighbors,
Number of neighbors, right? So the number of neighbors is called as K underscore neighbors here. Okay. I'm going with, say, 3 neighbors. By default, the number of neighbors is 5. Anything else that you remember? Sampling strategy, right? How many do you want to increase? So I'm going with 1. So what it will do is, so I'll show you before and after. Okay. So before, the ratio is this much, counter of this out. And after, let me print this, after I apply SMOT and resample, this is this much. Let me call it resampled out. Okay. So I'll just copy paste this. So do you see that now the samples have increased?
Yes.
Yes.
So minority has become 35. Okay. 015 has become the 035. Okay. I'm going to do this. Okay. Plotting, I'm going to plot this data, and then you will see, okay, the differences between the two. Okay. I'm just going to plot it within here itself. Now I want you to visualize, see a lot of purples are created which were not there earlier.
Yes.
So this was normal oversampling where there were 70 samples. See how many samples are here now? 70, right? 35 plus 35.
Yes.
Okay.
Yeah.
But do you see that now the purples have been created? New purples have been created.
Yes.
Yes.
Okay. So this is how your SMOT works. Let's see if SMOT is helping here. Okay. So currently the example that we have, do you think SMOT helped? Just by looking at it. With respect to this, do you think SMOT helped? In my opinion, it did.
Yeah. The
Okay.
visualization itself.
See,
Yeah.
this sample would have been misclassified regardless, right? Yes or no? If you look at this sample, would have been misclassified regardless.
Yes.
Yes.
Because when you draw the logistic regression boundary, this would be on the wrong side. Okay. But now that maybe if the line is shifted, see, there yellows are more, right? Yes or no? So the line
Yes.
would be more closer to yellows. Okay. Okay, line would be more closer to yellows. Okay. Or I would say that it would try to perfectly, I mean, it would try to at least, and yellows, the line would be away from yellows. My bad. Line would be away from yellows. So anything below this line would be yellow. Okay. So because yellows are more, they will be favored more. And some of the blues would also be misclassified. This yellow cannot be identified correctly. Why? Because, I mean, if you draw a line here, this is misclassified. If you favor yellows more, then a lot of blues would get misclassified. Yes or no?
Yes.
But this time you have like more data for purples as well. So maybe only a few misclassifications, like for this, it would happen. Okay. Let's see how much is the number of total misclassifications. So let me call it SMOT over sample data. Okay. Let's do the, you can say, model training with and without. Okay, let's fit our model onto your original data, which is an input and output. Okay, and let's, I'm going to look at training accuracy. Okay, this is just to show you, okay, because I haven't created a test set. Okay, or maybe I can use the test set, the top 2 features from it. That can be done. So I'm going to basically get the predictions on my train set. Okay, so these are my predictions on the training set. Let's get the accuracy. on the training set. So this is just to show you on the training set, this was the accuracy before. Okay. So predictions are here, actual values are here. Sorry, actual values are in out. So this is your train accuracy. Okay. So it's around 0.94. Some of the samples got misclassified. If you want, I can highlight those samples also. This is without oversampling, without any sampling, let's say. Okay. Let's do it with SMOT. Okay, so this was resampled input and resampled output. Okay, this is resampled out. So this is just to show you. Okay, hopefully SMOT helped. Okay, it actually reduced it. So maybe what I'll do is I'll do no regularization. Okay, so currently in logistic, the penalty is L2. Okay, I'm going to say there is no penalty, and the penalty is none. Okay, 1 second. Let's see if this helps. I just have to write like this. 1 second. It's small ny. Okay, it's 0.92. Do you see that it got reduced?
Yes.
Okay, so because it was regularizing, so it kind of gave, I mean, an underfitted model, a slightly lower complexity model. Okay, and do you see that now? If I give no penalty, which is better? Yes,
That
sir.
time, yeah, that time the
Not-
resampled was
0.9 to 0.9.
yeah.
You see that like here SMOT helped actually. Because the penalty was L2, right? So it was kind of giving you the results for that data set with, I mean, deliberately penalizing a good model. Okay. And the alpha is also very high by default. Okay. So you can just compare these raw results, I should say. Okay. And you can see that, okay, it typically helps. Okay. So this was about train accuracy. If you want to get the test results, you can do that also. I'm going to print. So let me call this as train ACC. I'm going to get the test results as well. I'm going to use the entire test set. So test set is this. And let me print both train and test. I can just format this. Okay, that would be easy. Did I miss something?
Should I give only X-test 2 features from this X-test?
Yeah, thank you. No, but you're right that okay, I have to give 2 features. That is okay. The first 2
And
features.
its T is small. Okay, that is small only in this case.
Small only, right? Okay, let's see. There's a problem somewhere. Maybe bracket comma problem is there.
Comma.
And there is this comma problem here as well. Okay, so this is the train and test accuracy. Okay, see, I'm choosing very few samples, right? How many samples are there in my training? Actually, 50 only. Do you remember I chose 50 random samples? Okay, so that's why the test accuracy is low. Let's see after doing SMOT if it helped or not. Looks all right, right? Any other changes? No, right? Okay, so in this case, training accuracy improved, but test accuracy kind of decreased. Okay, so what I'm going to do is I'm going to use SMOT on the entire data set. Okay, see, obviously, for the amount of data that we are increasing, right, it is possible that the test results, see, I have to look at the distribution of test data also, right, to make a clear judgment about it.
Yes.
If you just increase with 50 samples, it's not going to help much. Okay, in this case, it deteriorated by almost 0.7% or maybe close to 1.2%. Okay, I'm going to show you. Okay, for different values of the sampling strategies, it can help. Okay, so I'm going to find the best model. Let's see, and let's see. Okay, how much? I mean, how much we can make it better. So I'm going to use all the data this time. Let's maybe do this. Okay, this would be easier. So make my own pipeline and do all of the things that we did earlier. Okay. All right. So my sampling strategy is this. So instead of calling here random oversampler, let me call SMOT here. Okay. And we can try for different number of neighbors. So I'm going to try for, say, maybe say 2 to 7. Okay, 3 to 7. Okay. I'm going to try for 3 to 7, maybe at 2 intervals. Okay, at an interval of 2. Okay, because I'm doing binary classification, it doesn't make sense to use odd, right? Do you remember it?
Yeah. Yes.
Right? Okay. All right. Okay, looks all right. So for standardizing, then using this, then calling the pipeline. Do you want me to run a grid search? It will not take much time because the data is small.
Yeah, so we can go for
Okay,
grid.
let's go with grid. Yeah. It shouldn't take much time. Okay. So this would be param grid.
Can we do with logistic penalty as none here also?
Yeah, you can specify the penalty as none here. Okay. I mean, you can try for different penalties if you want. Yes or no? You can try for different penalties. So, but then you have to ensure that if you're using different penalties, you have to call the appropriate solver.
Yes.
That I think there is only one solver which is called as Saga, which works with every. Yeah, I mean, you can be okay. Then I would have to go with the randomized search. Okay, because then it will start taking time, because for different values of L1, L2, right, we have to provide alphas also.
Yes.
And ratio also. Yes
so
or no?
let's go with one none only and then we can try that.
Okay, but you get the point, right?
Yes.
So maybe I'm going with just the default values of these alphas and L1 ratio. Okay. So I've just set the solver as Saga. Okay, let's see this. Hopefully this will not take much time. Okay. It is fitting. Okay. It is just showing you convergence warning. So it means that you can increase the number of iterations. Okay. I mean, one suggestion that I would have is increase the max ITR here. I'm not going to run it. I'm just keeping it for you guys. Okay. You can run it in your free time. Maybe have, say, 1 lakh iterations. Okay. It will stop quickly. Okay, it's not going to run for much longer because I have 10 here. So 3, 5, 7, 3 here, 30, 30 into 4, 120, 120 into 5, almost 600. Okay, so 600 total warnings you will see if it is not converged 600 times. Okay, so it is done. Okay, so this is your best performance, best score. Around 97.89. We did it for other methods also, right? But we didn't run grid search. Okay, but can we actually see if it is improvement upon those or not? We ran randomized at CV, right?
Yes, we do. This
What was the result for this?
you scroll down.
It is 97.54. Okay, here it is even better. Okay, like just not much, but 0.25% better. Okay. And this is the best params for you. So it is L1 penalty which is helping, by the way. All right, but if you provide different values of alpha, it can give you even better results. Okay. So this is about your oversampling, undersampling. Any questions? Shall I show you different variants of SMOT?
Yeah.
Okay, let's do different variants of SMOT. Yeah. So I'm going to show you like one of them, and then you can try with the remaining. Okay. Which one do you want? These are the different variants on the left-hand side, if you see. On the left-hand side, if you see, these are the different variants.
K-means.
K-means,
Okay.
yeah.
Okay, let's go with K-means SMOT. Okay. See, K-means SMOT will not help you visualize though. Okay.
Okay, on that time, then we'll use a different one, because if the visualization was there, then it will be.
No, the visualization I can create if you want. Okay.
Oh, okay, okay.
This method will not give you anything special. Let me see. Okay, if in the properties, okay, if in the properties you have that. All right, let me just check. Okay, so these are some attributes. It is not returning the clusters explicitly. Otherwise, they would have plotted it for you. Okay. So this is a threshold. It's the fitted k nearest neighbors. Okay, that is fine. So k means estimator. Okay, I think I can still do it. Okay, I can plot the visualization for you as well. Okay. Let me try this. Let me try this. You can see there are different methods: sampling strategy, random state, k neighbors within a particular cluster. How do you decide like which sample should create? I mean, a new synthetic sample or not? Okay. So let's try with this. So oversampling technique. Let's import this K-means SMOT. Let's call this as KMS. I'm going to do it with the visualization only. So let's say the sampling strategy is 1. And a random state to ensure we get the same results. Okay, and then I'll just take the whole thing. I'll just call it resampled input, resampled out. Let me print before also. So this is the before ratio. Okay. After resampling it, this is the after ratio. This is the plot for the afterwards data. Okay. So this is what it does. Maybe it looks very simple to, because the data is not kind of what we say is overlapping, right? So you may see, okay, it's the same thing. Do you see any changes with respect to the regular SMOT? This was the
No.
regular SMOT. Okay. There are certain changes that I can see. Okay. There are certain changes that I can see. Okay. So what I'll do is I will, do you want me to create a shuffle data? I mean, do you want me to create overlapping data and then show you, okay, how it turns out to be different? Do you want to create data which kind of overlaps?
Yes.
Okay.
Yes.
So I'll do that. Okay, that can be done. Okay. So to create this data, we need to create it. I'm going to create it synthetically. Okay. Let's go with our own data set. Let's try for the number of samples. Sorry. So I'm making the 50 samples. Okay, these are the number of features. So 2 features. I want informative features to be 2, redundant to be 0. Okay, I want 2 classes. I think it's called as number of classes. I also want weight. It's called. So how many samples do you want in the majority class out of 50? Shall I take 40?
Yes.
Wait. Okay.
Okay, so 40 of 50 would be 0.8. Okay, all right. And I'm going to add some noise. Okay, so that samples are kind of flipped as well. Okay, so I'm going to add say 20% noise so that you can see. Okay, so maybe it's a 10% noise is enough. Okay, I think it's called as weight or weights. I have to check. And this is fine. So this is your input and output. I don't think I have to change anything else. All right. This is again, it's called as weights. Okay. So this was the original ratio. Do you see that there is overlapping now?
Yeah.
I want you to, so this is not the original data. Do you want me to plot the original data first and then the oversample data so that you can side by side?
Yeah.
Okay. So this is the oversample. Let me plot the original as well. And you can see that the data, by the way, is generated in clusters, right? If you can see carefully, the data is generated in clusters. So here. Let me say this is your original data. So, okay, what happened? Do you see any differences between the two? No, right?
Yellows have increased at the top right.
Yeah, yellows have increased, right? Okay, so yellows were actually in the minority. No, but yellows are in the majority, right?
Yellows are one was the minority.
Right, yeah, so ones would increase. Yeah, you're right. Ones would increase. Okay, I wanted to see that. Okay, where they are increasing, there are actually more yellows. Do you see that for this yellow, no increase was there?
Yes.
Okay,
Yeah.
but for other yellows, wherever they are in the majority, it got increased significantly, right?
Yes.
So for this yellow and this yellow, you see that, okay, it did not increase. Yes or no?
Yes.
Does that make sense? But let's say if I do SMOT, right? For this point, you might see some yellows here. So shall we do a simple SMOT also?
Yes.
Yeah. Yeah.
So let's do a simple SMOT also. Okay. So let me do simple SMOT also here. Let me call it SMOT input output. Okay, so this is for your k-means. Let me see if there is any error that I have to check. I don't think so. Okay, let's see. So this is the data. Okay, for k-means mode, you will not see samples being generated for this yellow. Okay, do you see for this yellow there are no samples being generated? I'll just reduce it. Okay, look at for this yellow first. Okay, there are no samples, right?
Yeah.
And there are no samples in between also here and here. Okay, do you see that samples are actually getting generated in a cluster? Here only, in the dense regions. Okay, now I want you to see normal SMOT. Look at this. Okay, here also some data is generated.
Yes.
Okay, so it is kind of looking at the nearest neighbors, maybe this point, and making one in the middle of it. Maybe it's looking at say this point must have been I would say that maybe this point with respect to say some other point, maybe one of them, it got I mean not here. Okay, let me think. Okay, how was this point being generated? That's a tricky thing. And based on the orientation, how is this point generated? I have to think. Okay, I can't say for sure. Okay, but I hope you get the idea. See, you can see new points being generated in these regions. Okay, even when yeah, you can. Do you want me to add more noise so that you can see? Okay, with the yellows that are kind of highly encapsulated, no points would be generated. Do you want me to, I mean, even induce more noise just to see?
I think it's clear
Yeah.
from this thing only.
It's clear from this thing also? Okay.
Yes.
Okay. All right. So this is your, I mean, different variants of SMOT. So you can try it out and see k-means SMOT and SVM SMOT, and even that adaptive SMOT. They are kind of the best performing ones. Vanilla version of SMOT can fail. Okay. Especially when the number of samples are large. Okay. So it doesn't yield good results. We are still taking only 50 samples. In our data, we started with 50 samples only. Okay. So do try out these other strategies and maybe observe the results. Okay. Any other questions about this? Yes. Any other questions about this? Is this clear?
Yes, Anton.
Okay. All right. I'll go to the next topic then. So our next topic is called as, so our supervised learning is done basically. Okay, our supervised learning is done. I'm going to show you your syllabus and you can tell me if anything is pending or not. Just a second, my browser is loading. You see, I've tried to cover almost everything in way more detail than what is mentioned in your curriculum. But if you still feel I have missed out something, do let me know. Okay, start from here, module 14. Is there anything that I have missed? Look at this particular module. Is there anything that I've missed?
What are these 6 jars?
Okay, so
Yeah.
this is generic
You
terminology.
told in the starting also that.
Yeah. Now, this is a generic terminology. So, okay, think about this. For machine learning, what do you require? How do you decide, okay, what machine learning algorithm you're going to choose? So, what is the first thing that you would see?
The performance of a model
No,
on
what is the first thing? Okay, how do you decide what model you are going to apply?
Based
distribution
on
of
the
the
distribution of a data.
The data.
data?
The data is one of the jars. Okay. Now,
Okay.
looking at the data, you will decide, okay, you are going to do regression and classification, right?
Yes.
Okay, so that is called as a task. That is the second jar.
Okay.
Does that make sense? And then you will decide what type of algorithm you will pick.
Okay.
Okay, that's the third jar. Okay, think about how do you evaluate a model?
Different metrics.
That's one more jar. Okay, think about how do you figure out the you can say parameters,
The hyperparameters for the models.
the hyperparameters, right? You tune them, right?
Yes.
Yeah.
You tune them. So how are they tuned? They are tuned on the basis of some loss function, right?
Yes.
The fifth jar. Okay, and there is one more. Okay, let me think. Okay, so this is like a basic terminology. Okay, nothing special. This is like
Okay,
basic terminology. Nobody is going to ask what are the 6 jars for ML. Okay, but anyways, let me show you. Okay, I'm forgetting this the terminology. Okay, 1 second. I'm forgetting there is this 6th jar. If I have it here, I'll probably show you this. Yeah, here it is. Did I miss anything? We talked about the data, the task.
the model.
Well, I think we missed the model, right?
No, we covered model.
Model also, yeah.
So then we covered all 6 then. We didn't miss anything.
We missed learning, I think.
Learning, I think we missed.
The loss function that you optimize. Oh, sorry. Learning is essentially the optimizer that you apply to the loss function. Okay, think of linear regression. What is the loss function? Think of linear regression. What is the loss function there? The squared loss. You have, we talked about multiple variants of loss functions, right?
Yes.
We talked about ordinary least squares, mean squared error, mean absolute error, right?
Yes.
We only used squared error or maybe say variant of squared errors.
Yes.
That loss function, right? Because why? Because they are differentiable, right? And how did we learn the optimal parameters from it? So we saw 2 different methods, right? One was simply differentiating it and equating it to 0. And then we solved the linear equations. Another was we used gradient descent, right? And then we had a discussion about the matrix-based solution also.
Yes.
So learning is nothing but optimization technique that you use to solve for the parameters of the loss function.
Okay.
Okay, so that's like the optimizer that runs. Okay, it's a generic term. Okay, it's a generic term. It's not, I mean, something that they will ask you in the interviews. Okay. Okay. Anything else? Okay, let's go back to the syllabus. Look at first the module 14. Okay, is there anything that we have left out? By the way, expert systems. So previously, machine learning models, when they were used in an application, they were called as expert systems. Okay, so don't get confused by this terminology. So back in the days, around 30 to 40 years back, people used ML algorithms and like decision trees, and they called them as expert systems. So they used it for decision making processes. So back then they were called as expert systems. Now we call them as machine learning algorithms. Okay. So there was no formal machine learning domain as such. Okay, but there were algorithms which could do predictions back then. So I believe that there is no topic that I have missed here. Okay, what about this one? You've covered everything, right? Here also.
Yes. Yes.
Yeah.
What about this one?
Owning.
Covered.
There is no leftover.
Thing, right? I have gone beyond why. Beyond. Okay, look at this. I think for every model, I've already spoken about do's and don'ts. Okay, I've already talked about how do you compare and given you additional resources as well, so that you can use those packages and
Yeah.
make a selection based on say 10 folds or even say one split using lazy predict or say PyCharacter.
Yes.
Okay, I think we covered all these.
Yes.
Yes.
Okay, so only 3 of the modules are remaining. So this is the last module related to ML, and then we will start NLP. So I will be here up to this part. So essentially, if you think about it, we have around 6 sessions remaining. Okay, but I'll try to cover it over a period of 2 weeks so that you get extra details as well. Okay, so I'm planning to cover this today, market basket analysis. Okay. So any questions before we start this?
No.
Shall we start?
Yeah.
Okay. All right, so let's start with an introduction to unsupervised learning. Let's have, so if time permits, I'll start market basket also. But we need to have this huge discussion about it. Okay. So unsupervised learning is a domain where you don't have any outputs. Okay, where you don't have any outputs. So I'll just show you maybe some examples, and then you can tell me what is it that you can extract from it. Okay. So let's take a look at a small data set. I'm going to show you a visualization of, say, a data set with, say, 2 features. Okay. So essentially what you're given is a data set like this. Let me show you a small data set. Okay, don't relate it to regression or classification. Okay. Maybe I'll just import the input and output like this. Give me a second. Okay, I'll just. So I'm going to show you a sample data set. Okay. Don't think of it as oversampled or whatever. Okay. This is some data which is given to you. Okay, let's say this is some data which is given to you. What is it that you would want to identify from this? Can you think of something?
The relationship between X1 and X2.
Okay, that is one thing. Relationship between X1 and X2. Okay, let's note it down. I'll whatever you suggest, I'll show you everything. Okay. Relationship between X1 and X2. Relationship between the features. Okay. Anything else comes to mind?
Values of X that are like for X1 or X2 that are most occurring ones, or general behavior of X1 and X2 separately.
Data sign, I mean, you can do the data analysis part, right?
Okay.
Like basic things if you want to extract, like which values are occurring more. Okay, you can find out the maximum values, or you can plot for individual features also, right?
Yes.
Okay. So you can see the distribution of values in X1 through a histogram.
Yes.
Okay, that you can do. Okay, I'm saying if somebody gives this data, okay, your purpose is to do something of predictive nature. Machine learning is all about making predictions, right?
Yes.
Yes.
So think of something which you can use to make predictions. What is it that you can use? Okay, I'll give you some hints. Imagine that you have every dot as a customer. Okay, X1 is let's say maybe say the age of the customer. X2 is the salary of the customer. Okay, now what do you think you can do with this? Okay, maybe let's talk about these points. Okay, maybe they can give you an idea.
Outlier, that is also like.
Can I say they belong to a different group altogether?
Yes. Yes.
Okay, I mean, obviously outlier detection is a good point. Okay, but can I say that grouping is one of the things that we would want? Because if I can group these samples in a group, okay, then I can say which samples are closer to each other and which are not. And the people which are closer, I can give them the same ads, same suggestions, same recommendations.
Yes.
That will be predictive nature, right? Predictive nature. Okay. Now think of, as you mentioned, outlier detection. So I can also identify outliers with respect to you have done some techniques for outlier detection, right? What are those?
IQR.
Interquartile range. Okay. You have done standardization.
Yes.
We talked about Z-score.
Yes.
If the value of the magnitude of standard, if the magnitude of standardized value is greater than 3 or greater than say 2.75, don't you think I can call it as an outlier?
Yes. Yes.
So that we have also seen. Okay, but we'll do more techniques as well. Okay, by the way, there are grouping techniques which can help you determine outliers. So we'll do those as well. Anything else comes to mind? Think. There are many things that you could do. Okay, one idea is to find similarity, right? Yes or no? You have thought about the features. Can we not do similarity between the samples? I mean, one way is we are doing that for an entire group, but don't you see that we can do it for between the samples? Like, so which technique that we have seen before which finds similarity between the samples? Nearest neighbors.
Yes.
You can use these features to compute the distance between them, right?
Yes.
Talking about
Yeah.
the predictions, okay? But you can still use the similarity between the features, the distance between the features to identify how far two samples are. Okay, and you have known about multiple distance metrics. So we will use that. Okay, now let me give you an idea. Imagine that. Okay, let me make a small suggestion to you. Okay, and you tell me if it's a supervised data set or not. Okay, imagine that I give you some transactions. Okay, so there are some transactions. In every transaction, there are some products. In every transaction, there are some products. Okay, so there might be a lot of these transactions. Let's call them as TN transactions. And in every transaction, there are certain products. So you can think of it as watching movies. You can think of it as watching, listening to songs. You can think of it as buying stuff from Amazon or Flipkart. Okay. So P1, P2, P3 are products. Okay. So if a customer, let's call them as a customer or a transaction. Let's say these are customers. So if a customer has bought a product or watched a movie, you see it's a 1. Otherwise, you say it's a 0. Okay. So if I ask you, if this is the scenario, okay, if this is the scenario, how much similarity would you say is between customer 1 and customer 2?
2 out of 4.
2 out of 4, right? Okay,
Yeah.
that makes sense, right? Okay. So they buy they buy 2 products which are similar. Now, one question is this: if this is the scenario given to you, what can you do with which are things of suggestive nature? If I give you such a data set, what can you do with the help of this data set that can be of suggestive nature? And you see it actually in any e-commerce platform. Such data sets are used very widely. Okay, first of all, let us discuss this. Am I having any output as such?
No.
No.
There is no Y as such, right? So if there is no output, right, you can call it an unsupervised data set.
Yes.
Okay. So supervised learning comes from the fact that for every input, there is a specific label, specific output. Okay. Here, we don't have any outputs as such. That's why the term unsupervised. So did you see, I did not even give colors, right? If I gave colors, that would mean they are having outputs.
Yeah.
Yes.
Okay. So we are talking about unsupervised learning now. Let's say this is an unsupervised data set. So what can you do with this unsupervised data set? Think about it.
If I have a customer C3 for whom I have to predict like what product he will buy, then
Okay.
I can see if he is going to product P1, then P1 he will have a chance to go to P3 and P4 also.
Let me make this for you. Okay, let me make this for you. So, okay, let's say this is what it is. Okay, this is what it is. Okay, which product do you think C3 should buy?
C3.
P3.
Which product do you think C3 will be buying? Look at only these 3 customers to make a decision. Okay, which is more similar to customer 3, 1 or 2?
Similar.
One, right? And one has bought something which C3 hasn't bought. What is that product?
P1.
P1.
P1, right? So don't you think we can suggest P1 to them?
Yes.
Okay, that's like a similarity based outcome, right? So what is it that we did? We did recommendations.
Yes.
Okay, so that's the fifth point that we'll do. So we can make use of similarity. We can make use of grouping to do recommendation systems. Okay, all right. Think of something else that we can do. So you just found out the similarity between the customers. Think of doing similarity between products across the customers. Okay, if I give you P1 and P2, okay, the two columns, okay, when would you say that, okay, P1 and P2 are bought frequently with each other? When would you say that P1 and P2 would be bought frequently with each other?
When P3 is not.
No. Think about P1 and P2 only. Forget about P3 and P4. You're looking at these columns, P1 and P2.
P4 is bought, right?
No. I'm not talking about P3, P4. Okay, forget P3, P4. Just look at these P1, P2 columns. What would you do if I ask you that, let's say P1 and P2 are frequently bought with each other? How would you compute this?
Customer 2 is buying.
No, forget about customer 1, customer 2. Assume that I give you these two columns. Okay. So currently, how many times P1 and P2 are bought together?
1.
1 out of
3.
3 times, right? That is self-evident, right? Only customer 2 buys them, others don't. Okay. So do you think that if I give you these whole two columns, you can figure out just by checking when P1 and P2 are bought frequently out of the total number of transactions?
Yes.
And if this is a big number, what will you suggest?
That if somebody is viewing P1,
You can
then
suggest them.
predict P2 also to that customer so that he can see.
Makes sense, right? Okay. So that is also one way of recommendations. See, previously you did it customer wise, right? Yes or no?
Yes.
Doing it product wise. So I'm essentially looking at the similarity between the buying patterns of customers and then making recommendations, right? Make sense? You can view it from both different ways, right? Yes or no?
Yes. Yes.
So currently I'm looking at the similarity between the columns. Okay. This is called as market basket analysis. This is also a part of your recommendation systems. Okay. Now I want you to think in more directions. So imagine P1, P2, P3, they are movies. Okay. They are movies. And now you're given only the data of customer 1. Okay. Forget about the other customers. Okay. Forget about the other customers. Okay. So you're only given this data. So a customer has watched these movies. You know what these movies are. Maybe say the first movie is, say, Inception. Okay. Second movie is, say, Batman. Third movie is, say, Avengers. Fourth movie is something else. Okay. Something like that. My question is this. How would you make recommendations based on the movies a person has watched without looking at the data from others? Think. You can come up with some nice ideas.
The categories into which these movies falls, like if it's a fiction movie or it's a comedy.
So it's a genre, right?
Yeah. So that
Right.
genre movie will be recommended to customer C1.
So did you use any data from the other customers?
No.
No, right? Okay. All right. This is called as content-based recommendation. Look at the content of the movie, the products, and suggest new products to a customer. Okay. All right. Now, what other things that we can do? We can look at actors, we can look at director, we can look at how much the movie made on the box office. Okay. How much, what rating it had, right? So if I have all these information, don't you think I am only using the content of the movie the customer has watched? I'm not using data about any other movie, right? Any other customer also. Only the movies which a customer has watched. Based on those, I'm making a suggestion. This is called as content-based. Okay. Now, there is something called as memory-based where you are going to use the data from all of them. And we just spoke about it, right? Okay. I'm just giving you all the things which you can probably. So if you start reading on your own, right, you will see all these things. Okay. So content based is only about the content of a customer. Memory based is when you are going to utilize the data of everyone else. Okay. And in memory based, there are again several, you can say, different branches. So one of the branches is called as collaborative filtering, where, okay, do you remember we talked about the concept of dimensionality reduction? Do you remember we talked about the concept of dimensionality reduction? Reducing the number of features.
Yes.
Okay. So my question is this. Okay, how many products do you think will be there in the catalog on Flipkart? What is your best guess? So if you look at, let's say, Netflix, how many movies do you think they will have in their catalog?
It's too large.
Too large, like just give me a number. Okay, let's say 10,000. Okay. So you essentially, can I say that the data is represented with 10,000 features?
Yes.
Okay. Now, did I show you that proof that if you have large number of features, it is difficult to find samples as the nearest neighbors? Did we discuss it?
No.
Okay, then maybe I'll talk about that. Okay, when we start with this particular topic. So the idea is most distance-based learning algorithms, they don't work in high dimensions. So algorithms like k-nearest neighbors, linear regression, wherever you're using some notion of distance, right, these algorithms will fail miserably in high dimensions. And that is why we want to reduce the number of features. That is one more reason to reduce the number of features. And the number of features in such type of data set would be very, very large. So let's say you have n customers and you have, say, D features. Okay. So you have n samples and let's say you have D features. Okay. Now I have a question. Look at this. Okay, I'm going to decompose this data into some parts. Okay, let's say I'm going to decompose it into, say, n comma k, and then k comma k, and then say k comma d. Do you think it makes sense I can factorize this matrix into 3 new matrices? Yes or no? Does this make sense or not? Do you think if this is the data that is given to me, which is n comma d, can I factorize this data into these 3 parts? Can you see the dimensions? Are they compatible or not? A matrix which is of size n comma d, can it be factorized into n comma k, k comma k, and k comma d? Yes or no? Is it possible?
Yes.
Okay. Now assume that k is smaller than d. Don't you think I have just reduced the dimensionality?
Yes.
Okay. This is called as matrix factorization. Okay. This concept is called as matrix factorization. And this particular factorization technique is called as SVD, singular value decomposition. We will see how this technique can be used to make recommendations in lower dimensional space. So I want you to look at this matrix n comma k. Can I say this is the matrix where I have number of customers multiplied by the new dimensions? Look at this matrix n comma k. N samples comma k.
Yes.
Okay, comma k features. K, these are the k new features. Okay, this is n comma k. Okay, this is some n comma k. I want you to tell me, can I say that I have just reduced the data from D features to K features?
Yes.
And now don't you think I can do the distance in this K feature space?
Yes.
So that is like checking out the similarity between the customers in this reduced feature space of size K. Now think about this K cross D. Can I say that I have represented each of my products in terms of these K new features? Can I say that each of my products? Okay, look at this K cross D. Okay, look at this K cross D. How will you interpret this as? Just take the transpose of it, maybe you will get an idea. Don't you think I can write this as, view the transpose of this matrix. Do you think I can write it as D comma K, the transpose of this? Okay, now think what is this? What is this matrix telling you in English? Can I say that you have D features, sorry, D samples and K features? What are these samples now? Look at the data, the products.
Products.
Okay. Can we say that each product is now represented in terms of feature? Yes or no? Does that make sense? Previously, how many features were required to represent a product? Carefully see. So if I take the transpose of this matrix, what is the size of a product? N, right? N would also be a large number.
Yes.
So if you were to compute the similarity between products in the original feature space, it would be quite cumbersome, right? It will not give you good results. Because I just said that if you have large number of dimensions, the results are very poor. Distances, they fail. Okay. The notion of distance doesn't work. I'll show you a proof for this. Okay. So is it okay to say that I can use this matrix K comma D, or say D comma K, to find out the similarity between the products also?
Yes.
Okay. This whole concept is called as collaborative filtering. Okay. So based on this technique of matrix factorization, you are reducing the dimensions of your features and products, okay, into a reduced feature space. So previously, you can say your customers were represented in terms of products and products were represented in terms of features. Both values are very large. Now you have reduced them into into very insignificant sizes. I shouldn't say insignificant, but small size. Okay, so because the feature size is small, then you can get the distance computations in those small number of features in the small feature space. What do you think a hyperparameter here is in SVD?
K.
K, right? So you can get different results for different values of K. Okay. So we will talk about it's just that K is a hyperparameter. You try with 10, 20, 30, 40, 50, whichever gives you good results, go with that. Does that make sense? Okay. So we'll see. Okay, we'll implement all of these things. Okay, we'll implement all of these things. Yeah, so these things are not in your syllabus, by the way. I'm just letting you know. A recommendation system with collaborative filtering is not there. Outlier detection is also not there. Okay. This we have done, by the way, relationship between the features. Do you remember? Has anybody taught you correlation? Has anybody taught you correlation? What is correlation? I think I have also.
Yes, like it's the how much one feature is related to the other feature.
Right. And what is the range of correlation? -1 to 1. Do you remember this?
Yes.
1 means that the features are, the vectors are along the same direction. -1 means that they are exactly
One
opposite.
increasing and other decreasing.
One other is decreasing. 0 means that they are independent. You know about this, right? So you can get the relationship between the features using correlation analysis. That is one way to do it. Okay. Now, what I've just described is something called as dimensionality reduction. Okay, reducing the dimensions. So this is one more concept that you can think about. Okay, reducing the dimensions. So some of these concepts, they overlap. Okay, some of these tasks that we are doing, they will overlap. This is also not a part of your curriculum, but I'll show you some techniques with the help of which you can reduce the dimensions. I'll not go into the theory part. I don't have that much time for it, but I'll show you all these things in the next class. Okay, so if I forget, just remind me. Okay, just remind. So this is what is about to come next. Any questions as such? Probably we'll discuss the next topic tomorrow or on Monday. So we have 2 more weeks remaining to finish your, you can say, the balanced curriculum, the pending curriculum. Okay. Any questions as such? Yes, people, any questions as such? All good, all clear. Great. We'll see everything in detail. Okay, we'll see everything in detail. All right. Okay. So I think that's it. I'm done for the day. If there are no questions, I'm done for the day. I mean, I don't want to start the market basket analysis, which I thought I would do today. But maybe I'll show you a small data set. Okay. And okay, I'll show you a small data set. I'll go to say ML extend. And I need this. So this is a new package that we'll be using. Imagine this is a data set. Okay. Let's say this is a data set. You can think of each row to be a product. Okay. So this is your data set. Okay. This is your data set. So you can see that, okay, the first customer buys apple, beer, rice, and chicken. The second one, can you just give me a moment, please? I have an urgent call. Just give me a minute, please. Sorry for the interruption, guys. So if you see this data set, okay, you can see some customers are buying these products. So every row is a transaction. My simple question is this: is this data set unstructured or structured? What do you think? Are you aware of structured representation and unstructured representation?
Structured.
This is actually unstructured. Okay, let me describe what unstructured and structured are. Structured means a tabular data set. Okay, so okay, let's try to understand it from this perspective. If I ask you how many times or if this particular row contains apple or not, what would you do? You can actually see, right? But you have to figure it out through a task. How would you do it?
I'll see the first element of the list, and if apple is present in that first.
Okay, if not present in the first position, then you will go to the second element and so on, right?
Yes.
So you are searching in it?
Yes.
Okay, so if you are going to search in your data, right, to find the relevant information, okay, then it is an unstructured data set. Okay, as simple as that.
Okay.
If it involves searching, then it is a unstructured data set. I'm going to show you another representation. Please see to this carefully. So I'm going to make it like this. So this is, say, transaction 1 or customer 1. This is transaction 2. Okay. Now let's think about each product. So apple is 1, beer is 1, okay, rice is 1, and then chicken is 1, and then you have bananas. Okay. All right. Now, which products the customer has bought? The first one, apple has been bought, beer has been bought, rice has been bought, chicken has been bought, but bananas, no, right? Is there any product that I missed? Is there any product that I missed?
No.
No, right? Okay, the 5 only, 5 unique products. Okay. Now, my question is this: if I were to ask you that in the first transaction, in the first row, is there apple or not? What would you do? Will you check for others?
No.
You will just check here, right? So did you search? You did not, right? You just went to the desired memory location and you got the result, right?
Yes.
By looking at the element here, you can actually identify if it was bought or not. This is called a structure. It's a tabular representation of your data. So both data are the same, right? Yes or no? Aren't these data the same? Is there anything which is not present in this structured representation, which is present here, or vice versa? Don't you see that they both contain the same information? Okay, if I ask you if the previous one contains in the first row, is there bananas or not? Don't you think you can identify it?
Yes.
But here I can identify it directly, right? It is just the difference is how you retrieve things, right? Yes or no? The difference is how you retrieve things. My question is this: which type of representation do you think takes more space?
Structured.
Structured one, right? Absolutely spot on. Okay, this type of representation takes way more space than the other one. Think of on the scale of Amazon or Flipkart. Okay, you guys will be not even able to import the data. Did I take your pre-boot? Was I the instructor for your pre-boot sessions?
Yes. Yes.
Yeah.
Then I spoke about this in detail in that time also. Okay, so this is called as unstructured representation. So the idea here is like if you have smaller data sets, then you prefer structured. If you have larger data sets, then you prefer unstructured. Okay, so you will be making such design choices and you will be making your programs. But in your course, we will be only dealing with structured. Okay, it's not about unstructured at all. By the way, you must have done a little bit of MongoDB, right?
Yes.
So you know how to deal with unstructured data through NoSQL. Okay, don't you think you can get all the details if I give you this table and you store it as a SQL file? You load it to your, load it as a table in your, say, MySQL platform or any SQL platform, any database management system, and then you can do the processing with SQL only.
Yes.
That is also possible, right? So structured data is, the name itself is SQL, right? Structured query language. So it only works with structured data. NoSQL works with unstructured and semi-structured data. Okay. So when we are going to deal with the data that is given to us, right, we will preferably transform it to structured because we are comfortable with pandas and everything. Okay. So there is this library called as MLExtend. Okay. This library, by default, it is not there. This library is called as MLExtend. Okay. Machine learning extensions. Okay. This is called as machine learning extensions. Okay. Yeah, the X here stands for this. Okay, they write it like this. Okay. So this library can be used to convert any unstructured data to structured type. Okay. By the way, in sklearn also there is a way to do it. I'll show you both. Okay. In sklearn also there is a way to convert this type of data to this type. Do you want me to do it today or in the next class?
Next.
Okay, let's do it in the next class. Okay. So you can install MLExtend and we will see it in the next class. And I'll show you the alternative method in sklearn also. So in sklearn also you can do this conversion, okay, from unstructured to structured. And there are other things also in this, what we say, in this MLExtend library. There are a lot of these things that we are going to study. So this concept of market basket analysis, okay, is going to be covered with the help of this library. Okay. So the market basket analysis concept, we will touch with the help of this library, MLExtend, machine learning extensions. Okay. So this is the second most important library in your curriculum after sklearn. Okay. We'll see this in the next class. Okay. So I'll stop here. Any other questions? Yes, people. Any other questions? Okay, if there are no questions, then you guys can leave and I'll close the session.
Thank you.
Bye, everyone. Take care. Enjoy your weekend. All right. Bye.